5 of the lecture on infinite impulse response filter design, analysis, implementation. And this is the University of Texas at Austin, spring 2014. So I wanted to start off with, with demos today, we've got slides today, we've got a handout, so lots of things going on. So the handout I've also made available electronically. I'll send you an email about that. So this was something you may have remembered from signals and systems, and that is that we can implement a transfer function in cascaded form and also parallel form. And they each have their place. You know, more commonly, I've gone with a cascaded implementation for a number of reasons, but for speed and parallel and make it more parallel, you go with the cascade, and I've also done that too. So let's take a first order example. 2 real poles for our case. They could be complex, and it just makes the arithmetic more complicated, but that's also fine. So I have a 2-pole filter, so I have poles P0 and P1, P0 and P1, and I can write this a couple ways as a transfer function to do that. And for the cascaded implementation, I'm going to break this into 2 first order filters. No, so I'll email this out. So I have two pole locations, P0, P1, so I can implement the second order section. I can always do it as a biquad, certainly, but just for simplicity, I went with 2 first order filters here. So I can do a cascade of 2 first order filters, H0 and H1. H0 has pole location P0, and H1 of Z has pole location P1. Okay, so it's cascaded. So what I've done is I've factored the transfer function into 2 first order terms. All right, so I've factored it as H0 of Z times H1 of Z, where H0 of Z is 1 over Z minus P0, and capital H1 of Z is 1 over Z minus P1. So it's just factoring the second order polynomial into 2 first order, the denominator really, or factoring factoring a second order transfer function into 2 first order transfer functions and implementing them in cascade. An alternative to this, which does get used in practice for speed reasons, is for the cascaded implementation, as the way I've drawn it, I have to first apply H0 before I can apply H1. Right? So I have to apply H0 to the input signal X of n. It produces an output signal. Then I can go ahead and filter the output signal of H0 with filter H1. There's a delay incurred, an extra delay step, where I have to go through a first order filter and then another first order filter before I get to the final output value. So there's a faster way to do this, which is parallel implementation, and this is where partial fractions came in. This may be something you remember or not, but in partial fractions decomposition, I can take a higher order transfer function and break it into a sum of lower order sections or lower order transfer functions. So here I can break the second order section into the sum of 2 first order sections, which is different from a product. And in partial fractions, I can use Mathematica, I can use other software tools to do this. There are some algorithms by hand if you wish, but I'd rather use something else that can do it for me. So here's partial fractions, so I take the same transfer function as I had earlier. So this term already factored for me. And I write it in partial fractions form. And I get a sum of 2 first order sections. And so in terms of the block diagram, I have a sum of 2 filters. So the input X comes in. In parallel, it goes through 2 first order sections. And I sum the outputs together to get the output Y of n. And why is this faster? When is it faster, I should say? It's not always faster, but when is it faster?
The architecture has multiple processors.
When the architecture has multiple processors, or a more general way to say it, when I can implement G0 of Z and G1 of Z in parallel. So a field programmable gate array might do this. On our programmable DSP, we have no advantage. It's a sequential processor. We don't have enough, unless we're multi-core, but on the one that, if we just use a DSP core, there's no advantage here. The DSP core doesn't allow us, in floating point, to parallelize this to be any faster. So that doesn't really help us. But on a field programmable gate array, we can do these two in parallel, and that means I can run these twice as fast as if they were in cascaded form. Go ahead.
So are you saying that also the reason why we keep it in factored form so that we have use less memory as well?
The factored form has the advantage that essentially I'm filtering before I'm filtering, right? So I'm filtering by H0 before I filter by H1. So I can, goes back to quality factors and things. So I can choose carefully the ordering of these sections so that I have a better outcome in terms of the implementation from input to output. I'm closer to the filter that I really want, but I have the ideal filter. In the parallel case, not so lucky, because in the parallel case, what I have is I don't have any filtering before filtering. So every section is just done in parallel. I have no way to, say, attenuate the input signal before I hit a section that's more oscillatory. I don't have that option that I would have in the cascaded version. So this is a little riskier because the Q factors could be very high. And I don't have any control over how I filter before a section that might have higher oscillation in it. So the parallel form has some downsides. I mean, the good side is it's faster. The downside is I don't have a lot of control over what happens in each section.
Well, I was just saying, because if you like multiply everything out, then you end up getting like decent negative 2, and then you end up having more initial conditions to keep track of.
Well, I still have an initial condition here, and for this case of a second order transfer function, realizes two parallel first order filters, I still have an initial value of an initial output here and an initial output here. Still two initial conditions.
Oh, okay.
And then for I only have trivial zero locations, but so that's I'm fine here. But so I don't change the number of initial conditions. Both forms have the same number of initial conditions.
Well, yeah, I thought if you just like multiply everything together, then you could end up getting like decent negative 2 rather than decent negative 1. But I guess.
Yeah, it's the same. It's the same because ultimately we're implementing the same transfer function. Right? It's the same second order transfer function. Okay. So whatever happens here has to happen in the two realizations. Right. So I have Okay, so on the slides for lecture 6, this is part 5 now. So we're up to a bunch of demos in FDA tool in MATLAB, in the filter design and analysis tool. So we're up to slide 6-26, I guess. Yeah. So I have a series of demos, and we'll see the limitations of these different filter design methods, and there are several. All right, so let's take the first one up. So this is running FDA tool with default parameters. With sampling, so let me get this over here. So sampling rate 48,000, passband 9600, stop band frequency at 12,000, and so forth. Passband ripple 1 dB, stop band ripple at stop band attenuation at 80 dB, as you see here in the parameters. That's the default. So if we go ahead and I'm showing you the magnitude response from the analysis menu. So if I run the Parks-McClellan, also known as Remez Exchange, and here it's called equal ripple, lots of different names, for the default FIR design. So if I want to do minimum order, which is already here. So I do the minimum order design, very quickly we see, does it meet spec? Does it meet the specification in the stop band? No. So it's above 80 dB. It doesn't get down below 80 dB, so we have to increase the order or find some other way to meet the spec. Okay, so one way to go about it is I'll try to change the order, and in changing the order I can also play with some weights. Now these weights tell me how much emphasis do I place on the pass band or the stop band. And we saw that the failure was in the stop band. So I'm going to put a little more weight in the stop band. All right, and I'm going to also crank up the order here to 100.
Is there some kind of like unit of measurement for the weights? Or
The weights are unitless.
Just
it's a relative weight. So basically there's an error that you incur in the pass band, there's an error you incur in the stop band. The question is, which one are you going to try to reduce more than the other?
The algorithm.
With algorithm operates, that's right. So here's the 100th order filter weighted, and now do we meet spec? Yeah, we're pretty good. We're way below. I don't have to zoom in, right? We're way below 80. And we should probably zoom in the passband. And where's the passband here? It's up to 9600 hertz. It looks pretty good. All right, so that's in, it's between plus or minus 1 dB from 0. So that's good. All right, now, this is great. Now, this is way more than we need, so I probably can reduce the filter order. But what I'm going to do next is try to break the algorithm. Why not? All right, so let's try the order of 200. So a 200th order filter should be a better filter. It should be even better. It should have a much lower stop band attenuation, and it does. It's now down to the minus 180 maybe range. It's pretty amazing. All right, let's try order 300. Now I've already given you the hint. This doesn't converge. Yeah. Okay, so it tells you. So this is the algorithm now. This is just trying to find the coefficients for the FIR filter to meet the specification. And it says failed to converge after 2 iterations. And if we look at the MATLAB window, we don't get the warning there anymore. So it's all up in the depends on the version of MATLAB. All right, so here's all the warning up front. And so it says, and you can kind of see it doesn't give us a very good looking filter here. It's certainly nowhere near the spec. So our stop band attenuation at the stop band frequency of 12 kilohertz is maybe 15, 16, 17 dB. So it didn't get very far. So try to iterate. Also look at what happened in the passband. I get this incredible ringing, and there's some. What's this? What the heck happened here? Yeah, there's there's no input here. We're just designing the coefficients. All right, we're just designing the coefficients to give us an impulse response. Resonance would mean that there's an input that it's resonating from. Now, if I did input something at wherever this frequency is, so let's call it 9.7 kilohertz, then I would get resonance out. I'd get an unbounded output out. Right? So that's not much of this isn't much of a filter if you haven't figured that out. Something has gone, first of all, it didn't converge, so we can't really rely on this answer. But if we look at it, it's got some basically incredible amplification of this frequency. And the amplification at about 9.7 kilohertz is about 15 dB.
Would we, if we were for some reason to say, let's just use this filter, would it function if we were to just only pass frequencies that were close to DC or really high frequencies?
Well, who knows if maybe there is some use in the world for this kind of filter. Sure, what you would do is you basically have a narrow. You could look at this as a narrow bandpass filter that amplifies frequencies around 9.7 kilohertz, has mild attenuation at low frequencies, about 15 dB down, and a little better, but still not so big. Maybe from peak here, it goes from 15 dB to minus 15. So about a 30 dB of stop band attenuation at higher frequencies. Okay. I mean, who knows? It may have some use out there. But this is not what we wanted. This is not the kind of filter we were seeking to design. So what happens? All right, so my Parks-McCollum algorithm fails on me to give me coefficients back. I want a filter. We got backup plans. So we look at, let's try Kaiser. And so let's try minimum order Kaiser. Let's find the window. Kaiser, I can choose many options, but here's Kaiser. And let's see if this meets spec. If it doesn't, we got it. Ooh, we may not have met. So it was incorrect. So it does not meet spec. We're in a little bit higher order than 101, right? So if we need, where's my stop band frequency? Yeah. So anything above 12 kilohertz needs to have less than minus 80 dB of attenuation. So I fail. Looks like I fail right here at 12 point, a little above 12. Okay. So whatever version I was using on my laptop gave me a different answer. So let me see what we can do here. No, yeah, that's fine. Let's try. Let's try 200th order FIR filter. Yeah, it's not really impressive. We can play with beta. We can play with some different things to get a better order. Or what else can we do? We go back to Kaiser.
Is that cutoff frequency supposed to be?
That cutoff should be the midpoint, and it wasn't. That cutoff should have, well, it is a midpoint. It's a midpoint between passband and stop band. So we can, so if we're off by, let's go back to the design we had. So if we're off by, how many dB are we off by? Not much. Less than 1 dB. So what do you do?
We just increase the stop band.
Right, increase the stop band attenuation. Let's go to 81 instead of 80. And it looks good now. Yeah. And we increased by 1 order. So it's 102nd order instead of 101st. Yeah.
So are all of these iterative?
Kaiser's not iterative. Kaiser's a formula. Parks-McClellan's iterative, and least squares requires it's not iterative, but it requires a matrix inversion. So it's a formula, but it's a matrix formula. This one is a scalar formula for Kaiser.
So for the equiripple, did you have just increased the number of iterations when you put the order as 300? Because it said in the warning.
I'd have to change this filter specs to get convergence, but probably at about 300, the Parks-McClellan algorithm will have difficulty in double precision floating point. Certainly by 400, my experience is it's over. All right, it's just beyond what it can do because for whatever reason you get numerical precision issues. All right, so here we meet spec at 102nd, an order of 102 instead of 101. So that's good. So Kaiser is a good backup plan when Parks-McClellan doesn't converge and least squares doesn't converge either, or gives you a numerically. It's not convergence in least squares. It's the matrix inversion that's involved gives you an ill-conditioned answer. So if neither gives you what you need, Kaiser is a good backup plan. If you have to design a filter on the fly in the embedded system, where you don't have the luxury of running Parks-McClellan on a microcontroller or a DSP, but Kaiser nicely is a formula, and you can actually put that in you can actually encode that on the DSP, which is nice to design filters on the fly. All right, let's do next slide. Next set of demos. So now we do IIR filters. And let's go back to original spec. We want IIR, and I want elliptic. Eighth order. Now again, these nice thing with the classical IIR filter designs, Butterworth, Chebyshev, and elliptic are closed form formulas. There's no matrix inverse, there's no iteration. Direct closed form. And the order calculations come from finding roots of a polynomial that's used in those design algorithms. So the filter order is just really accurate. I haven't seen it fail over these years. Okay, so this is eighth order elliptic. Let's see if it meets spec. Yeah, right, dead on. Okay, so dead on. It's coming. Yeah, there's some surprises. All right, so let's look at the pole zero plot. Yeah, and you've seen this on the homework. So it's a low-pass filter, and you see the cluster of pole locations at low frequencies. And if you figure, again, what is this pole angle here? What's your guess, given the filter specs? Remember, poles tell us the passband. Well, give it to me in radians per sample. Just give me the full, without factoring it on me. So it's 2 pi times the passband frequency divided by the sampling rate. And so how do we convert a continuous time frequency to discrete time? Multiply by 2 pi and divide by the sampling rate. And this is lecture 1, right back in sinusoidal generation. You'll be with us the rest of the semester. Fundamental. So that angle should roughly be 2 pi times 9600 divided by 4800, roughly. All right. So, because usually the poles are in the pass band and the zeros are in the stop band. Occasionally you might see a zero in the transition band. That certainly can happen. In fact, it's happening here. So where's the stop band attenuation? The stop band frequency in hertz is 12,000. The stop band frequency is 12,000. What is that in radians per sample? Pi/2. Right. So the stop band frequency is right here. You'll notice there is a 0 in the transition band. And there's also a 0 very close to pi/2, but to the left of it. So zeros tell us the stop band, and the poles tell us the pass band because they're separated at an angle. Remember, the poles and zeros get too close. They have interplay and interference. They change the game here. But when they're separated at an angle, we can very quickly get that this is a low-pass filter and kind of eyeball what the pass band and where the stop band and pass band frequencies are. Now, there are two poles very close to the unit circle, and that's going to be an issue in implementation. That's very close. Go ahead.
For sanity's sake, could you remind me what is the effect, just in general, just in a single pole, what is the effect of a single pole on the response of the system, like the effective response?
Right. So remember, the pole impacts the denominator of the frequency response, and so to evaluate the magnitude of response, say at this frequency, it's 1 over this distance to the pole. So when the pole gets really, really close to the unit circle, that distance gets really, really small, and the magnitude gets really, really big. Okay. And if the pole is on the unit circle, it's no longer bibostable. I have an oscillator. And if the pole is outside the unit circle, it is bibo unstable. Go ahead. It's bibo unstable, but also blows up. If it's on the unit circle, it's bibo unstable and oscillates in terms of the impulse response.
So, if you were to, like, say, you give him like this filter and be like, it's running unstable.
Once you implement it.
Yeah.
Yeah.
So you want to move? Would you, if you wanted to move the pole in, would you just attenuate the frequency that I think that pole's at?
So you got a couple options. One is you can manually you can use the pole zero tool here. I forgot the name of it now. It's a pole zero editor diagram. It's one of these. There you go. Pole zero editor, and you can actually manually move poles around. Or you can, as we'll see shortly in the next set of demos, we can constrain the pole radius to be no greater than, say, 0.92 or something. Now, that constraint may mean that the filter order has to increase, but we get which is not intuitive, we can get a 10th order filter that's easier to implement than an 8th order filter in terms of stability after implementation. It's more complicated because I have 2 more poles. There's more multiply add operations per sample, but the trade-off is it's less likely to go bibo unstable when implemented.
What's that? The radius you say? Like, what is that? More meg?
Well, it's a rule of thumb, but 0.9 is pretty safe. Right. The higher the radius, the more likely that pole would become, after implementation, an oscillator.
So is that a coefficient in the difference equation? Just like the radius?
Well, you can expand the poles, and the pole and zeros give you the factored form, and you can expand that to the unfactored form to get feedback and feed forward coefficients. So the poles give you the feedback coefficients, and the zeros give you the feed forward coefficients.
Okay.
All right. Now, by default, FDA tool puts the IIR filters into second order sections, a cascade of second order sections, which is the safe way to go, as opposed to one big direct form structure. All right. Now, if you notice, I've got 4 conjugate symmetric pole pairs, and I have 4 conjugate symmetric. Sorry, 5. 4. Yeah. So or 8th order. So I have 8 poles. And they're arranged in 4 conjugate symmetric pairs. So here's a conjugate symmetric pair. And the 0 locations are also, I have 8 of them, and they're in conjugate symmetric pairs. Right, so I have the one here, close to pi/2, and there's its conjugate symmetric version. Now that's for 8th order. For 9th order, so we can increase this to 9th order. And now you see I have a real pole, right? So with 9th order, I have 4 conjugate symmetric pair poles, 4 symmetric pairs of poles. I have 1 real pole. And among the zeros, I have 4 pairs of conjugate symmetric zeros, and I have a real 0. No.
Is the main reason that they're always going to be like that is because if you didn't, then you would have like imaginary components in your equation.
That's correct. So we want, that is to say, we want our feedback and feed-forward coefficients to be real valued,
Yes.
and this will get us there, right? So if I were to come up with the first order section, which I need to do, I have 1 pole, what 0 would I pair this with? Our rule of thumb said get the 0 that's closest in distance, but that wouldn't be such a great idea because now we would have a complex valued feed-forward coefficient. So which 0 would you like on this one over here, right? So you could modify the rule of thumb. If I have a real valued pole, I really want to team that with a real valued 0, so that my first order section gives me a real valued output for real valued input. There were some other hands up I didn't catch.
Well, I was just going to say, that pole that's real, it isn't a double pole, is it?
No, it's not. In fact, in these filter design algorithms, I have yet to see a double pole happen using Butterworth Chebyshev elliptic.
So more generally, you're saying that like whenever it's an even order pole, you always have its complex conjugate, and then whenever there's an odd or pole, you will always have a real value.
1 real, that's right.
At least 1 real.
Yeah, yes. But the way so again, if I have a 9th order filter, I'll have 4 complex conjugate symmetric pairs of poles, 1 real pole. It's the way I've always seen it. And the way to think about it is I'm taking what is the passband range of frequencies, which is from roughly 2 pi times 9600 divided by 4800, which is somewhere up here. So this is my passband, right? I'm going to kind of put my pole locations around that. They're not uniformly spaced, even along an arc, but you can kind of see them that they're spaced out over the passband frequencies. So if I have an odd order, then I'm going to put 1 here on the x-axis, and the rest are going to be conjugate symmetric pairs. Same with the zeros. Now, manually, I can use repeated roots, and I do. So that if I design a filter by placing poles and zeros manually, sure, I can put a repeated root. And we do this in practice.
Have you ever seen an even ordered system that had 2 real valued roots?
That, off these filter design algorithms, I have not seen it, but again, manual placement, yes, absolutely. And we did this when we looked at biquads and looked at bandpass filters and band stop. So we did a band stop filter that both zeros were we were doing biquads somewhere in here. It was on this slide. The annotations are gone at this point, but it was on this slide, so it was lecture 6 part 2, and what we had looked at was if I had put, so here's my z-plane, and I wanted it's imaginary, and I wanted a bandpass filter. And I can put my pole locations here. Both are real value on the x-axis. Put my zeros up here, pi over 2 and minus pi over 2. Now I have a band stop filter at pi over 2. My pass bands are at 0 frequency. Remember the angle, the frequency is the angle with the axis. Right, there's your frequency. All right, there's your frequency. So this pole at z equals say 0.9 is means I have a passband at 0 radians per sample, and I have a passband at pi radians per sample. I have a stop band at pi over 2 radians per sample, and a stop band at minus pi. So this is stop band. This tells the 0 location tells us the stop band frequency, which is minus pi over 2. And the pole location tells me I have a pass band at 0 and pi radians per sample, n minus pi radians per sample. So there's both poles are now real valued, a very useful band stop filter.
So if you remove either the zeros or the poles, you'd still have the stop back.
Yeah, if I remove the zeros, I still have a band stop filter. It just wouldn't be as good of a filter as if I had my zeros where they are.
If you remove the zeros,
Yeah, if you remove the zeros,
What if you remove the poles?
also band stop, but not as good as it could be. Very wide transition region if you remove the poles. All right, so that's ninth order elliptic, also shown here. All right, now let's increase the filter order, which was your earlier question, to 20. Why not? It should be a better filter, right? So here's the magnitude response of my ninth order filter. Here's 20. Should be better, right? Oops, something's going wrong.
Why is this better?
Well, with more poles, you think it should be better. All right, so
wow, it's such a short.
so that's not so bad. That's just some there's some wiggle in there in the oscillation. So that's actually not 20 is not too bad. Actually, 20 is doable. 20 is. I'll break it with a little more order, I think. So let's go with pole 0 plot. And now we have a repeated root, which I have not seen before. It's interesting. That pole is basically, it's like super close to the unit circle. So that's going to go unstable with almost any implementation. In an implementation. So let's do, let's go with 30. Why not? Wow, that's, let's see what we get here. So I'm still not breaking it. I'll break it, don't worry. It's only a matter of time. I'm disappointed. All right, we're just going to go. How about 400? Yeah, all right. They didn't like that one. They wouldn't let me do 400. Wow, they're not letting me do even, preventing me from breaking. Oh, I don't need to do. Okay, got it. All right, I'll break it another way. All right, let's go back to 20. Now let's go. I'm in a cascaded form, so I have 10 second order sections, 10 biquads. Let's see. I need to go to convert to single section. There we go. So now it's direct form. No more biquads. We have a problem.
So the direct form comes directly from the difference equation, right?
Right. So I've expanded the pole 0 locations into coefficients. So I just have one big filter structure, one big tap delay line for the inputs and one big tap delay line for the outputs. And not much of a filter. I have a great oscillator now. My IIR filter is a wonderful oscillator. So in as a cascade of biquads, it was still stable, bivostable. Once I go to a big, direct form, it's bivo unstable.
So this is because you lose precision?
That's correct. You lose precision, and the coefficients, when you expand them out, you keep them in. You start with all the poles and zeros in double precision float. You expand them out, and each multiply, you lose 53 bits of mantissa, because you're keeping everything in double precision float. We had this discussion in an earlier lecture. So you end up with the feed-forward coefficients have a lot of error in them, because you're not doing the expansion in exact precision.
So when you say 53 bits of mantissa, that's worst case.
That's a 64. That's worst case. That's 64-bit. Right. So let's look at what happens on the poles and zeros. So we saw that they were inside the unit circle. So after we convert to 1. Should be something just in. There you go. 2 poles launched outside of the unit circle. So again, a filter that was stable when we had cascaded biquads, bivostable, converts to one direct form, Bible unstable.
This poles is outside the integral, or not the zeros outside the integral.
Zeros don't affect stability unless they cancel some pole that's unstable. Then there might be cancellation. In theory, in practice, it's hard to pull that one off. Yeah, zeros can be wherever they
Like a
want.
zero with a magnitude more than 1, I feel like that wouldn't do.
So zeros are not going to, zero locations are not going to cause us to be Bible unstable.
Oh no, I'm just thinking
But-
for general about like putting a 0 outside the unit circle. It doesn't seem like it would have any different effect than a 0 on the unit circle. Like
Well, zero on the unit circle actually will eliminate that frequency.
yeah,
On the zero away from the unit circle, if it's really close, it doesn't matter whether it's inside or outside. It's the distance from the zero to the unit circle that matters. So if the distance is the same, it doesn't matter whether it's inside or out
Okay.
much, and then in terms of its magnitude response. At the frequency of the zero, the magnitude response wouldn't change, whether the zero is inside or out. Now, as you go around the unit circle, whether the zero are inside or out does have a slight change at other frequencies. All right. So there it is. I should have followed my own directions. All right. So oscillate. So we got an oscillation frequency at 9 kilohertz. That's 15 dB above the passband. So it's pretty good oscillator. Not a very good filter. I remember these filter design algorithms for IIR design in terms of pole, zeros, and gain. So when you implement the filter, it's a lot easier just to keep your poles and zeros as close to their original value as possible. All right, last one, which was constraining the pole radii so that I don't have as much concern when I implement the filter. So what do I want here? Let's go back to minimum order. So here's a minimum order, and I remember I had this one pole really close to the unit circle up here. And so what I want, there is a setting that does this, and suddenly, that's not it. That's interesting. For some reason, it's not showing up on this version of MATLAB. I don't know why. But I do have the screenshots for this. So, again, so on my own, let's go back to, let's go back to slides. So there is a least Pth norm option under the IIR design options, IIR filter design options in my FDA tool on my laptop. So this is, you can pick a weighting in the stop band just like we did before. And the eighth order, if you remember from our original design, an elliptic filter of order 8 was able to meet the spec. If we limit the pole radii, then it changes the gain because there were 2 pole radii that are outside of this radius of 0.95. So by putting a limit on the pole radii, we actually need more poles to meet the filter spec. And so a 10th order filter meets it just fine. Right, that's right. And now we're pulling it back to 0.95, and 8 poles isn't enough to meet the spec. So again, the observation here is the filter order might increase, but it's worth it for a more robust implementation. Even though you have 2 more multiply adds, per output sample because I have 2 more pole locations. I have to add another biquad, in other words, at least. So I probably have more like 5 extra multiply adds in the extra biquad, but it's worth it because now, once you implement it, it's going to behave as you want it to. Okay, let me go through some conclusions on IIR versus FIR filters, and this is, I also talked about this in the homework 3 solution set that's online. And again, homework 3 is on the back table if you want to pick it up on the way out. So a few things to observe, got a few slides here to go through. For the same magnitude specification, if we just count, multiply, accumulates, then what we find is that the order of the FIR filter is much higher. And we saw this in homework 3. So in that problem 3.3 versus homework problem 2.3, the FIR filter order to meet the spec for the ECG filter was 61 for Parks-McClellan, and it was what for the IR case? What order filter was that? Elliptic. 10. It was 10. So the order is now way out. So it's 61 versus 10. So it's a big difference. Okay. Now in terms of so this would be, from homework, this was 60th order. I had 60 zeros. For the elliptic case, I had 10 poles and 10 zeros. Right. So I had 20 poles and zeros. The FIR filter had 60 zeros. In terms of coefficients, that means I had 61 coefficients for the FIR filter. I had 21 coefficients for the IR case in direct form. Okay, so basically, that's a case where I had 3 times as many coefficients for the FIR case as the IR case to meet the same magnitude specification. The minimum order design, Parks-McClellan for FIR filters, for linear phase FIR filters, and elliptic design for IR filters. Bibo stability, go ahead. The problem with IIR is that the problem with IIR is we have feedback. So the question is which one is more numerically stable. For the FIR filter case, any numerical precision doesn't feed back. Any numerical error doesn't feed back. So it just goes away in a finite amount of time. But for the IIR case, we get this feedback, and so all the errors just keep feeding back in, making things worse generally. Right? So, and that's why stability is a big issue, right? Stability is a big issue. Right, so the FIR filter is always Bibo stable, no matter how you could implement it in 3 bits. 3-bit coefficients, 3-bit input, 3-bit output. 1 bit, you could just do sine, and it still would be Bibo stable. It's amazing the FIR filter can.
Is that why it was impressive that someone designed the 30-order IIR filter?
Yes.
The stability is so.
Yeah, we had a presenter earlier this semester on the 30th order, and that was all biquads. Be careful, and it was done very carefully. But it's pretty amazing to get a 30th order IIR filter to work in, I think it was in 32-bit arithmetic, integer. Pretty amazing stuff, really. Okay, and of course, Bibo stability is a big deal with IIR filters. For linear phase, yes, with Parks-McClellan. If the impulse response is symmetric or anti-symmetric about the midpoint, and this will be true for Parks-McClellan, for Kaiser, for least squares. Yes, we have linear phase, and it's overall frequencies. But for IIR filters, no, we're not going to have linear phase. In fact, any implementable IIR filter will not have linear phase overall frequencies. We simply can't do it. However, the good news is the phase may be approximately linear over some band that you care about, and maybe that's good enough. We saw that in homework 3.3. Elliptic, Chebyshev, Butterworth all gave us linear phase over some part of the passband. Okay, the choice, as a demo showed, the choice of the IIR filter structure really matters for both analysis and implementation. That the direct form, where the IIR filter is just one big tap delay line, or 2 really big tap delay lines, one on the input, one on the output, is really prone to numerical precision errors and prone to Bibo instability when implemented, even in double precision floating point arithmetic. So the IIR filter structure really matters for both analysis and implementation. The IIR filter design algorithms return list of poles, list of zeros, and gain or list of gains, as it may be. So we want to keep the roots, that is to say the poles and the zeros, in their original form as much as possible. We don't want to lose precision. So we want to keep roots computed by the filter design algorithms as they are. And so the good news is that if I give you a polynomial in expanded form, rooting the polynomial is very robust. I can find the roots. And there are papers rooting, a millionth order polynomials, and they're incredibly accurate. That's not the problem. The problem is the other way. If I give you the list of the roots, how you expand the factored form to unfactored form really impacts the errors in the coefficients of the polynomial. The order matters, and even the best order, you're going to lose something, because every time that we expand, we lose something in floating point. Right? So if I take the biquad case, which I've worked a few times before, so 2 poles, 2 zeros. I'll leave the gain off for now. All right, so 2 poles, P naught, P1, 2 zeros, Z naught, Z1. And if I expand this out, then I get 1 minus P naught plus P1, Z to the minus 1, plus P naught times P1 times Z to the minus 2, and the same thing, the same structure for the numerator. So this is just expanding the 2 poles and 2 zeros into unfactored form, and we'll notice right away that we get, when we do this multiplication, P naught times P1, well, those are double precision floats, and we multiply them, we put that result back to double precision float. So worst case, we throw out 53 bits of mantissa plus sign. The addition here isn't so bad, we just lose a bit, worst case. But now imagine think about a third order polynomial. It's P naught times P1 times P2. A fourth order polynomial, that coefficient is basically the product of all the poles. So once I have a 10th order filter and I go to this from factored to unfactored form in direct form and expand out just into one unfactored polynomial in the denominator and one unfactored polynomial in the numerator, this term is the product of all the poles. Every time I multiply 2 poles together, I throw out 53 bits. I multiply another pole, I throw out 53 more bits. So this is extremely inaccurate. As the coefficients go from left to right, I get more and more inaccuracy. And now if I were to then factor the resulting unfactored polynomial, my poles are moved all around. And many of them probably outside the unit circle. So it's this step, which is called polynomial inflation. That's what this is. That's what this step is. That's this expansion. That's where you get into trouble. So we limit the degradation of the root locations, the pole locations, by doing cascaded biquads. So we only expand 2 poles at one time, and never more than 2 in the biquad structure.
So we pretty much have to do this though when we implement our difference equation, right?
Right, because the biquad is the smallest order filter that gives you real valued feed forward and feedback coefficients. I can always do cascaded first order sections, but then everything's complex valued. And a complex multiply is 4 real multiplies, and a complex multiply and add is 4 real multiply add operations. So complexity just kills it. So we're better off doing the biquads, a really nice trade-off for both complexity and also controlling the expansion from poles to coefficients. There are more than 20 IIR filter structures in use. Direct form is very common. Cascaded biquads is very common. And lattice filter is the third that's really common. And you know, you can. I'm not going to test you on that. We didn't cover lattice, but it's something to go look up if you're interested. IIR filters beyond 12th order are really hard to get right, even with cascaded biquads when implementing them. It's really hard to get them numerically stable after implementation. Now, let me finish up the last slide on this. So cascaded biquads is the safest way to go versus direct form. And it's a matter of getting the right order of biquads, and if you have an odd order filter, then there's a real first order real valued section to include in the mix. Now it turns out that there are an awful lot of solutions in filter design you can go for, and the algorithms that you use pick one point out of a very large solution space of possible solutions. As we saw with constraining the pole locations, it turns out the minimum order design isn't always the best one to go with. for stability reasons. It also turns out that the minimum order is not always the most efficient. Now, this may also be counterintuitive. But it turns out if you increase the order, you eventually can unlock some very interesting designs where all the feedback and feed-forward coefficients, or actually half of them, to be more fair, are power of 2 coefficients. So I don't get a lot of precision loss when I use them.
Like you specifically arrange to like maybe like order 2 or 4 or 8.
You generally have to double the minimum order to get this one, from what I've experienced. So you have to go much higher order, but the good news is the feedback in the biquad structure, the feedback coefficients are half, fourth. I mean, they're power of 2. So they make the math much easier when I multiply. I'm just doing shifts, and I'm not losing precision, which is nice. I'm just shifting things around. Okay, so that ends lecture 6 slides, and thanks for coming. See you on Wednesday.